Now, you've seen complex numbers before, starting probably in an intermediate algebra class and then in maybe your first pre-calculus class. So I just want to remind you a little about a complex number. Complex number is when we take a real number and we add it to an imaginary number. So for example, like 2 plus 3i. 2 is a real number, 3i is an imaginary number. Now, imaginary involves I. So recall that I, there's two ways to think about it. You can either view it as the square root of -1, or I is the number we square to get -1. Because the problem is when we square real numbers, we never get a negative answer, right? But it turns out there is a reality where the square of a number is negative. And that sounds like weird. It's especially weird because we called it imaginary. When I think imaginary, I think about fairy tales like Snow White and the Seven Dwarves, like Thor, the god of thunder. Sorry if you think Thor's real, but this is a bad name. They shouldn't have been called imaginary numbers because they're very, very, very real. When you take two magnets and they attract each other or they repulse each other, that is I in action. We can't describe that in physics and math without the use of these imaginary numbers, with these complex numbers. When you flip a switch in your light, when you use your phone, when you flush your toilet, all of that stuff about the way electricity works, about the way pressure and plumbing works, it's all related to I. So I is all around us, but we just don't see it and feel it the same way we count 1, 2, 3, or we measure stuff. It's around us in a slightly different way in these electric fields and the way water tension and pressure work. So I is very important, complex numbers is very important. Without our knowledge of these, we would not have the technology we have today. All right, so review of this. So that's review part 1. If we keep playing with powers of I, like for example, if we take I to the 3rd power, well, that would be I squared times I, -1 times I is -I. If we take I to the 4th power, then we're gonna get I squared times I squared, -1 times -1 is 1. And if we take I to the 5th power, well, that would be I to the 4th times I, which should just be I again. And then we get this cycle going on. So this powers of I are periodic. And I mention this because sine and cosine are periodic, and it turns out there is a relationship between I and the sine and the cosine. They're both periodic objects in our reality. Other thing, reminder about working with complex numbers, adding, subtracting, multiplying, and dividing. So because I is a little bit different object than like 2, these are not like terms, and I cannot simplify this any further. 2 plus 3i is as simple as it gets. I can't say 2 plus 3 is 5 here because the 2 does not have an I, right? They're not like terms. So as far as adding, subtracting, multiplying, and dividing imaginary numbers, the add and subtract, that relates to like terms. So if we were to take 2 plus 3i as a number and say subtract from it 5 minus 2i, then we have to combine like terms and distribute the subtraction there. So 2 minus 5, those are like, that would be a -3, right? So these are like here and there. And then the 3i is like the 2i, we're subtracting a negative, so that's gonna be 3i plus 2i, so that would be 5i. And it doesn't get any simpler than that because these are not like. Multiplying them is a little bit more work. So if you take something like 2 plus 3i and you multiply by 5 minus 2i, you have to distribute. 2 times 5 is 10, 2 times 2 is gonna be a -4i, 3 times 5 is going to give me plus 15i. And then 3 times -2 is -6. I times I is I squared, and I squared is -1. So this right here, oops, I squared, is really -6 times -1, which is really a plus 6. 10 plus 6 is 16. I lose 4 i's, I gain 15 i's. Altogether, I must have 11 i's. So that number right there is the product of the two numbers above. If I come across a number like 3 divided by I, usually we don't like to have square roots. I is a square root in the denominator. And our trick with, say, like 1 over the square root of 2 is to multiply top and bottom by the square root of 2. So in this case, we're just going to multiply top and bottom by I. So this is equal to 3I over I times I, right? I'm multiplying top and bottom by I. I squared is -1, so this gives me 3I over -1, which is really -3I. So the number 3 over I is the same number as -3I, but this number is what we call standard complex form. Standard complex form is A plus BI. So some real number plus some other real number times the imaginary unit. I is called the imaginary unit. Sometimes division is more complicated than that. So if somebody said, what if you take 2 plus 3I, that's a 3. Let's make a better 3. And you try to divide by 5 minus 2I. It's not as simple as the problem above. So here I have to multiply by what's called its conjugate. And the conjugate of 5 minus 2I would be 5 plus 2I. And we'll see why that helps in a sec. Got to do the same thing with the top, 5 plus 2I. And let's clean up the bottom first. Now, in the bottom, I have basically, that's like A plus B times A minus B. And hopefully you remember from your algebraic career, that is the same as A squared minus B squared. The middle terms cancel themselves out. And that's what's going to happen here. I'll distribute it out all the way to double check. 5 times 5 is 25. 5 times 2I is plus 10I. Negative 2I times 5 is negative 10I, right? You can see those guys are going to cancel. Negative 2 times positive 2 is negative 4. But then I have an I squared there. So these guys become 0. I squared is -1, which makes this a positive 4, giving me a 29 in the bottom. And that's kind of a cool thing that always happens with when you multiply complex conjugates, you get the square of this number plus the square of that number. 5 squared plus 2 squared is that 29. And that always happens when you multiply complex conjugates because of that I squared and the middle terms cancel. So I no longer have an I in the bottom. Cool. In the top, I got to distribute all that. 2 times 5 is 10. 2 times 2 is 4 with an I. 3 times 5 is 15 with an I. 3 times 2 is 6. I squared is -1, so that's going to be a -6. So then I get, let's see, 10 minus 6 is 4. 4 plus 15 is 19. And if I wanted to make it look like A plus BI, that's a fine answer there. I would write it as 4/29 plus I times 19/29, or 19/29 times I, doesn't matter. So division with complex numbers is a little bit more work because you have to multiply top and bottom by the complex conjugate. And that right there is a review. I'm hoping you already knew all that stuff, or now you remember, oh yeah, I used to know that. All right, here is the wicked cool punchline of this section. The relationship between complex numbers and polar coordinates, it kind of boils down to this periodic function I here. And so I'm just going to state this relationship and then we're going to use it. And here's the basic relationship. It's called Euler's formula. And it says that if you take the number E, right, 2.7-ish, and raise it to the power I times some angle theta, that is equal to the cosine of theta plus I times the sine of theta. And I'm going to show you a graphical representation of this, and then we're going to use this in some calculations and see why this is a powerful realization. So we discovered this a few hundred years ago. It's super powerful. We wouldn't be able to do the things we do with cell phones without a relationship like this right here. This was like a huge breakthrough in mathematics. We didn't know about it then because we didn't know much about electricity back then, if anything. But it turns out this formula from a few hundred years ago was influential in our modern technology with like how cell phones work, for example, radio waves, things like that. All right, so I'm just going to pick an angle theta, and I'm going to use pi over 6. So I'm going to take a look at what does e to the I pi over 6 look like. Euler's formula says that's the cosine of pi over 6 plus I times the sine of pi over 6. All right, so this is one of those special angles we should be familiar with. The cosine of pi over 6 is the square root of 3 over 2 times plus I, and then sine is 1/2. So 1/2 I, or I times 1/2. So these three things all mean the same thing. So this is a complex number right here. This is a complex number right here. This is an alternate way to write them, right? So sometimes we write complex numbers as a plus bi, which is what I have here. A is square root of 3 over 2, b is 1/2. But now I have this alternate form for a complex number. Now, the form I wrote here, think about that for a second. Cosine lives between 0 and 1. Sine lives between 0 and 1. And graphically, what's going on here I can plot complex numbers by letting the x-axis represent real numbers and the y-axis representing imaginary numbers. Okay. So this is called the complex plane. It's a little bit different than the way we normally graph things, right? Because instead of x and y, I have real and imaginary. By imaginary, I mean the I part. So let's suppose that I put 1 here, and I go about that same distance up this way. The imaginary 1 is I. So if somebody said, hey, on the complex plane, plot I would put a point right here. If they said on the complex plane, plot 1, I would put a point right here. Somebody told me on the complex plane, plot, let's say 1 plus I. Well, here's 1, here's I. They meet right there. So that point right there is the point 1 plus I. Now I want to plot this point right here. That point right there, square root of 3 over 2. So let's see, if this is 1, square root of 3 over 2 is about 0.86. That would put me about right here. So that right there is about square root of 3 over 2. Half of I would be about right here. And so this complex point would be right about there. So that point right there is my square root of 3 over 2 plus 1/2 I. Now, cosine, think about that, and sine, I just plotted the cosine as kind of like an x value and I sine as a y value. So what I've done here is I've just put a point on the unit circle in the imaginary plane. So unit circle in the imaginary plane comes around like this through there. It's going to come down on this side. So this relationship e to the e to the I theta, excuse me, describes all points on this circle in the complex plane. So again, this is the complex plane here, a little different than our normal one, because instead of looking at x and y, we're looking at real versus imaginary, and we plot them as points. So I just plotted that point right there. Now think about this point for a second. Square root of 3 over 2 for x and 1/2 for y. That point right there has a radius of 1 and an angle of pi over 6, right? That's where we got this from. So this is going back to our relationship, our polar relationship. This right here is the rectangular version of this complex number. Rectangular complex number. And this right here is the polar version of the complex number. So that is a polar complex number. And this is polar because it describes the complex number using an angle. This right here describes the complex number basically using like X and Y coordinates. And that's how they differ. And they both have their strengths. So I'm going to demonstrate a strength of the polar version and how it relates to the rectangular version. I'm going to do that by looking at what happens if we take squares and square roots of complex numbers. So what I want to do is I want to take the square of this complex number. Now, when we talk about real numbers, our most favorite variable to use is x. When we talk about complex numbers, we often use the variable z. So in rectangular, the complex number z would be equal to a plus bi. Right, so that's the rectangular version. The polar version of z is some radius times e to the I theta. And I say some radius because the one above that e just to the I theta on its own is equal to cosine theta plus I sine theta. That's only going to give me a radius of 1. If I want another radius, I have to multiply that in. So that could also be viewed as r cosine theta plus I times r sine theta. And if you think back again to the relationship between polar and rectangular, remember that r cosine theta, that's how we describe x values in our original interpretation of trigonometry, and r sine theta is how we describe y values. Right? So this formula right here links polar and rectangular views of complex numbers. All right, so now for a square. So I'm starting with this number z equals e to the I pi over 6. Right, this number I was playing with up here and I graphed over there. Now I want to say, okay, what does z squared look like? Well, that would be the square of e to the I pi over 6. Okay, let's think about that for a second. We know power to a power means multiply the powers. So what happens if I take I pi over 6 times 2? So this is just e to the I pi over 6 times 2. Pi over 6 times 2 is pi over 3. So that would be e to the power pi over 3. And according to Euler's formula up here, that's equal to the cosine of pi over 3. Oops, I left my I out of there. Sorry about that. E to the I pi over 3. That would be cosine of pi over 3 plus I times the sine of pi over 3. And we should remember that the cosine of pi over 3 is 1/2. And the sine of pi over 3 is square root of 3 over 2. Let's graph that point up here. All right, so 1/2 for the real number is going to be about here-ish. And square root of 3 over 2 for the imaginary number, that's going to be about here-ish. So then I'm plotting this point right there. And what we should know about that point, again, I just graphed the point 1/2 plus I square root of 3 over 2. If I connect its radius here, its radius is 1, right? Because we know this is a point on the unit circle. And its angle, we also know, is pi over 3. So here's a wicked cool observation. If you think about this complex plane here, and you square a number in the complex plane, the polar version, its angle gets doubled. I square the complex number and the angle of that complex number in polar version gets doubled, right? Because that whole power to a power thing, which is kind of wild. So that's kind of a cool shortcut. The other way to square this number would be to square its rectangular form. So now I just want to point out that this was relatively easy given that I remembered these numbers here, right? If I take a power to a power, that means I multiply the powers and I get this new angle. So I jumped from the angle pi over 6 to the angle pi over 3, and I know the cosine of pi over 3 and the sine of pi over 3. I didn't really have to work too hard about that. I was just pulling a little bit out of my memory about how powers work and about sine and cosine. The other way to square z here is to square its rectangular version. And its rectangular version is the square root of 3 over 2 plus I times 1/2. And my claim is if we square that, we're going to get this red number down there. Let's see, square root of 3 over 2 plus I times 1/2. Squaring means multiply it by itself. No shortcut for that. You can't drop the square in there. It doesn't work. Square root of 3 over 2 plus I times 1/2, or I over 2, or 1/2 I, however you want to call it. And then I got to start distributing. So square root of 3 over 2 times square root of 3 over 2. Square root of 3 times square root of 3 is 3. 2 times 2 is 4. Square root of 3 over 2 times 1/2 I is going to be square root of 3 over 2. Oops, plus, sorry. Square root of 3 over 2 times 1/2 I plus 1/2 I times the square root of 3 over 2. Well, that's the same thing. Square root of 3 over 2 plus, oops, times 1/2 I. And then finally, I get 1/2 I times 1/2 I. So I times I is -1. So I'm going to get a negative. 1/2 times 1/2 is 1/4. Okay, let's clean this up some more. The real parts are 3/4 minus 1/4. That's going to give me a 2/4 or a 1/2. The imaginary parts here, let's see, that's going to give me square root of 3 over 4 I plus square root of 3 over 4 I. And when I add those up, I get 2 of them. And 2 over 4 is really 1/2, so that's 1/2 plus square root of 3 over 2I. That was a bit more work than the polar version. Polar version, again, I had to pull on my memory for this rule and those special values. But over here, I had to distribute, combine like terms, clean stuff up. But notice I get the same exact point there. All right, so next big rule, the extension of Euler's formula. So Euler's formula with powers. Oops. Powers. So the problem is if I take a plus bi and I raise that to some power n, that means I have to write that parentheses down n times and distribute. Now just the square was a lot of work, right? Imagine cubing this or raising it to the 5th power. Okay, so this is a lot of work. But the key is we have another way to write a plus bi. That is r times e to the I theta. And if we raise that to the power n, then what we get is, and again, this is a multiplication, so we can distribute that power. Powers distribute over multiplication, not addition. That's going to give me r to the n. That's not bad. And then it's going to give me times e to the I theta times n. Right? I just take n times that angle. In this previous one right here, we figured out that when we squared this polar point that had the angle pi over 6, the angle got doubled to pi over 3. Now the radius was 1, and if you square 1, you still get 1. So I'm still on the same circle on the complex plane here. And raising a single number to a power and multiplying an angle by a number is way easier than writing this thing out n times, like 5 times, and getting the answer. So I just want to look at this in action here. So we're just going to do a cube instead. So I'm going to take, let's see, how about, let's just take the number we had before, 1 plus I. And by before, meaning I graph that point right here on the complex plane. And then what I'm going to do is I'm going to cube it. So that's going to take whatever angle it had, and it's going to triple the angle. Right, so its angle is in here somewhere. So I'm going to triple that angle when I cube it. And then I'm going to take that radius, and that radius is going to get cubed out. So like if that radius was 2, the new cube radius would be 8. So it's going to kind of spiral outward is what's going to happen there. All right, let's do this. We can do it on this page. So my, first I'm going to start off with its rectangular representation because that's all I have, 1 plus I. Now I want to rewrite that with its polar representation, r times e to the I theta. That means I need to come up with r and theta, and that's an I there. Okay, so think about that for a second. So let's draw this over here. 1 I is this point right here, 1 plus I. The radius is the distance from the pole here, the origin, out. Well, that's just a right triangle, right? Our x squared plus y squared equals r squared. So the radius there is equal to 1 squared plus 1 squared. And again, we're just viewing this as a triangle. Forget about the I for a second. That's just 1 for a moment. 1 squared plus 1 squared is 2. So the radius is the square root of 2. So this point has a radius of square root of 2. All right, what about the angle there? So for the angle here, we know that this distance 1 is that distance is 1. So opposite over adjacent, that's tangent. So the tangent of the angle I want is equal to 1 over 1. So what angle do we know has a tangent, a slope of 1? Well, a slope of 1 goes with pi over 4, right? So we could double check. Theta equals the arctan of 1, and we'll find that, yeah, that's pi over 4. So the polar version of 1 plus I is square root of 2 times e to the pi over 4i. And sometimes I write I pi over 4i, multiplication is commutative. Who cares the order? Sorry if that's confusing. Okay, so now if I want to cube this number here, so if I want 1 plus I cubed, I have two options. I could write it out 3 times and start distributing, or I could just take this square root of 2 times e to the pi over 4i and raise it to the 3rd power, which means I'm going to get the square root of 2 cubed. Now remember, square root of 2 is the power 1/2. If I take the power 1/2 and raise it to the 3rd power, that's going to give me 2 to the 3/2 times e to the power 3 times pi over 4i. So that's just going to be 3 pi over 4. Now, square root of 2 is about 1.4-ish. Let's see what its cube looks like and see if this point ends up where I said it would. And I said, again, the radius would get cubed and the angle gets tripled. Calculator, please. Let's go to this GeoGebra here. And I'm not doing curves at the moment. So all I want to just double check is the square root of 2. It's about 1.4. And then now I have the square root of 2 cubed, which is 2 raised to the power 3/2. Okay, so that's about 2.8 or 3-ish. So my original point, if I do it in polar, the polar version of that point has a radius of square root of 2, the original point, and an angle of pi over 4. So I'm going to graph that here. And in polar here, I have to do it parentheses with a semicolon. And r is the square root of 2. Oh, my semicolon got in the wrong spot. And then semicolon, my angle is pi over 4. Okay, so here's my point 1i. GeoGebra doesn't know that's I, the I-axis, but I do. And then my new point, the cube of that point, we just calculated is, let's see, 2 raised to the power 3/2. And the angle of that point is 3π/4, right? So think about that for a sec. 1π/4 is here. 2π/4 is vertical. 3π/4 is over here, right? 3 times that angle. So 3π/4. So I have my radius got cubed and my angle got tripled. This point right here is the cube in the complex plane of the point I started with. Let's put that in paper. All right, so I'm going to summarize this on a new page here. We started with the point 1 plus I. And then we calculated using the idea that r squared equals x squared plus y squared, and theta equals the arctan of y over x. We calculated its polar version to be the square root of 2 times e to the I times π/4. And then we cubed that number. So we wanted 1 plus I raised to the 3rd power. And to do that, we took this polar version and cubed it. Square root of 2 e to the I π/4 to the 3rd power is 2 to the 3/2. You could just cube the square root, that works too. Times e to the I times 3π/4. Now, next thing I'm going to do is I'm going to put that in Euler's formula. Euler's formula says that the e part is the cosine plus I sine, and then this is just hanging on as a multiple. So I get that 2 to the 3/2 times the cosine of 3π/4 plus I times 2 to the 3/2 times the sine of 3π/4. And it's got to be cosine sine, because in the complex plane, we do the whole xy thing. So x is cosine, y is sine. Now 3π/4, we know that's a special angle. Cosine at 3π/4 is negative square root of 2/2. So this is 2 to the 3/2 times negative square root of 2/2. And then I have I times 2 to the 3/2. Sine, that's positive square root of 2/2. And this is going to clean up a bit if I view this as 2 to the power 1/2. So out front, I'm going to have a negative, and then I have 2 to the 3/2 times 2 to the 1/2 over 2. We'll clean that up, plus I 2 to the 3/2 times 2 to the 1/2 over 2. And when we multiply powers with the same base, we add the powers. 3/2 plus 1/2 is 4/2 or 2. And here in the bottom, I have 2 to the 1, right? So my new power is 2 to the 3/2 plus 1/2, 4/2, that's 2, minus the 1 down there, just gives negative 2 for the x value, plus I times the sine. What do we get here? Same thing, right? 2. And if we look back at that graph, we should see, oh, that's the point negative 2, 2. Negative 2, 2 for B here. Cool. So there's a lot of power in this view of the complex numbers. So the two big ideas here are that complex numbers can be viewed graphically. Oops, wrong button. Where we graph the real part of the number horizontally, and we graph the imaginary part of the number vertically, so that a plus bi ends up being a point in this complex plane. Other big idea. Euler came up with a formula that connects e to the I theta to cosine plus I sine of theta, which we can use to rewrite a complex number in a different form, and it makes finding squares and square roots easier. So we'll do a square root example next. So super simple problem. We know that the square root of -1 is I, but what is the square root of I? We're going to figure that out right now. To do that, we're going to use Euler's formula to play around with that. So what I want to do is I want to rewrite I as that polar form as r times e to the I theta. So I got to figure out what I and theta are. So let's think about, and then I'm going to take the square root of that. Okay, so I want to view I as r times e to the I theta. And there's a couple ways to do that. One way is to just think about the complex plane here. To plot I, right, this is the imaginary part, that's the real part. If this is 1 and that's I, oops, not question mark, sorry, I, then that's the point I want. Okay, what's the radius of that point right there? Well, the radius is just 1 because I is the imaginary unit. And what's the angle to that point right there? Well, it is pi over 2. So the polar version of I is radius of 1 times e to the I pi over 2, or pi over 2 times I. So 1 times anything doesn't do anything. So let's say that's e to the pi over 2I. So that's another way to write I. Okay, how does that help me? Well, I want to take the square root of I, which is the same as taking the square root of e to the pi over 2I. And square root is really the power 1/2. So that's really e to the pi over 2I to the power 1/2. Power to a power is multiply those powers. And so that gives me e. Pi over 2 times 1/2 is pi over 4I. So that's the polar version of the square root of I. I can put it in rectangular form by using that cosine sine relationship. So that's the cosine of pi over 4 plus I times the sine of pi over 4. Cosine of pi over 4 is the square root of 2 over 2. Plus I times the sine of pi over 4 is also the square root of 2 over 2. So the square root of this complex number right there, let's see, square root of 2 over 2 is about 0.7. So that'd be about here and about here. That's this point right here. So that point right there is the square root of I. Now, square root of 2 over 2, square root of 2 over 2, we know that's a point on the unit circle. So the radius of this point right here is still 1, which makes sense because this radius is 1 and the square root of 1 is still 1. What's the angle I have here at square root of 2 over 2 for x, square root of 2 over 2 for y? Well, obviously that angle is pi over 4. So the square root, so like a square doubles the angle in polar for the complex number, a square root cuts the angle in half, which is kind of cool. And that fits that formula I mentioned earlier, that extension of Euler's formula. Where the heck did I write that? I lost it. It was here earlier. Anyway, the formula that we had before, my pages are out of order. How did that happen? Okay, that explains it. So it's somewhere. Was that if we take something like r e to the I theta, and we raise that to a power n, that's going to give us r to the n times e to the I theta times n. And the complex version, or sorry, the Euler's version of that would be r to the n times cosine of n theta plus I times the sine of n theta. And that is a heck of a lot easier than taking the rectangular form and writing it down n times and distributing, right? Way easier here. Oops, I missed my r to the n there. Let's make that a little neater. Plus r to the n. So like a square doubles the angle, a square root halves the angle because the square root is the power 1/2, n is 1/2, half the angle. We can even do that for cube roots. So I'll do that in the next example.